Hello, my name is Andrew Ryazanov, and this talk is going to be about power codes which have near optimal convergence to channel capacity. And this is a joint work with Venkat Goswami and Min Yi. So we're going to be dealing with error correcting codes and communication in the presence of noise. So say we have Alice who is trying to send a symbol X to Bob, but this symbol might be corrupted by some noise in the middle. We will consider probabilistic noise, and the way we're going to model it is by introducing the channel W in the middle of this communication. This channel takes X as an input, and it produces some output Y in a probabilistic way, which means that for any input symbol X, there is a probability distribution over all the possible output symbols that Bob may receive. And this probability distribution is W of Y given X, and it is clear that the communication and the channel are completely described by these transition probabilities. All right, so the channels for us will be memoryless, which means that if we use the channel more than once, then every usage is completely independent from the others. We will also focus only on binary input channels. So the input alphabet for us will be bits 0, 1. The channels in this talk will be discrete, which means that the output alphabet is a finite set. And finally, we will assume that there is some symmetry underlying the channel. But I'm not going to go into details what that means, but the channels are going to be symmetric. And I will abbreviate this notion of binary input discrete symmetric memoryless channel as BMS channel. And this is the most general type of channels that we're going to consider in this talk. And these are the two most basic but fundamental examples of BMS channels. There is a binary symmetric channel on the left, which just flips the input bit with probability P. And on the right, there is a binary erasure channel, which doesn't have any flips, doesn't have errors. But what it does, it can erase the input symbol, the input bit with probability delta to be a question mark. All right, now when we have our definition of the channel, let's look closer at how communication usually happens in coding theory. So since the channel can introduce some non-trivial amount of noise, the way we handle it in coding theory is usually by introducing some redundancy into the message that we're sending. And specifically, say we're trying to send the message M of k bits, then we'll have the procedure of encoding who will take this message and exactly introduce some redundancy into it and produce a code word of n bits x1 to xn, where n is greater than k. After that, this code word is sent through the channel and we receive an output vector y1 to yn. And after that, there is a procedure of decoding who will take the output vector and try to produce a guess for what the initial message was. And our hope is, of course, that this guess is equal to the initial message M, at least with high probability. And if that happens, we call that the communication is reliable. So during this talk, we will only be interested in linear encoders, which means that the encoder just multiplies M by some k by n matrix A. And we'll be interested in codes, which are the set of all possible code words that we obtain at this stage. So all the code words that we send through the channel. And it is clear that in the case of linear encoder, the code is just going to be the row space of A. It is going to be a subset of f2 to the n, and the dimension of the subset will be clearly k. So k is called the dimension of the code, while we call n the actual number of bits that we transmit through the channel. We call n the block length of the code. And then the very important parameter of the code is its information rate, which is here k over n. And this is because we are actually trying to send k bits of information, but we send in n actual bits through the channel, and which means that essentially we send in k over n bits of information per one usage of the channel. And clearly, we want to maximize this rate so as we use the channel in the most effective way. And this is a very important task in coding theory, to find coding schemes which maximize this rate at which communication happens. And there is a very fundamental theorem by Shannon, who proved that any channel W has a parameter of capacity, I of W, such that the maximal rate at which you can push information through the channel W is exactly I of W. So it establishes the limit at which you can use some channel to communicate information. And specifically, it is possible to construct codes which have rate arbitrarily close to capacity. And on the contrary, if you try to push information through W with rate exceeding this capacity, then the communication becomes unreliable. And moreover, this can be stated in a more quantitative way. What Shannon proved is that if you want the code to be epsilon close to capacity, to have rate epsilon close to capacity, then it suffices for it to have block lengths of order 1 over epsilon squared. This is something that we call quadratic convergence to capacity. And the way Shannon proved it is by showing that random codes or random linear codes actually achieve this. So if you take a random linear code with these parameters, then with high probability, it will allow reliable communication. However, there are several issues with random codes, and some of them is that they are non-constructive, so you cannot explicitly specify them. And then you do not actually have any efficient decoding algorithms for them. And the best we can do is exponential time, which is clearly not efficient. And a natural challenge that arises from this is to actually construct explicit coding schemes with somehow fast encoding, decoding procedures, which allow communicating at this maximal possible rates. So this coding scheme should have rates approaching the capacity. And there has been several examples of codes that actually achieve this challenge. But today we will only focus on polar codes. So polar codes were introduced by Arikan in 2008, where he proved that they achieve capacity in the limit of large block length. And he showed that they can be constructed in polynomial time and that they have fast and encoding and decoding algorithms. And moreover, in couple of years later, in two independent works by Gulfami Chia and Hassani Al-Shahi Urbanke, it was shown that for polar codes, if you want to get epsilon close to capacity, it suffices to take the block lengths to be polynomial in 1 over epsilon. And this is something that we call polynomial convergence to capacity. And so far, the polar codes are actually the only family of codes for which we know provably this polynomial convergence to capacity. And this is why they are so powerful and so interesting. And in the second work by Hassani Al-Shahi Urbanke, it was actually shown that the degree of this polynomial, this mu, can be bounded by 6. And it was later improved by Mandeli, Hassani Urbanke to something around 4.7. And just as a notation, we will say that if n scales as a polynomial in 1 over epsilon, then the degree of this polynomial, this exponent, we will call the scaling exponent. And this just corresponds to how fast the codes approach, the rate of the code approaches to the capacity. But from the previous slide, we know that random linear codes actually have the scaling of block lengths of order 1 over epsilon squared. And there are converse theorems which show that this is the best scaling that you can get. And if the code achieves capacity, then the block lengths must be of order 1 over epsilon squared. So this is the optimal scaling of the block lengths that we can get if the code achieves capacity. Or in other words, the best possible scaling exponent that one can get is equal to 2. And it is achieved by these non-constructive random linear codes. And then the main question that we were answering in our research is it possible to achieve this optimal scaling exponent of 2 with polar codes or some variants of polar codes? And this brings me to our main result, where we prove this constructive, quantitatively strong version of Shannon's theorem and show how to construct explicit codes with this almost quadratic convergence to capacity for an arbitrary BMS channel. And this is our result stated a little bit more formally. You can see that our codes can have rates epsilon close to capacity, while block length is almost quadratic in 1 over epsilon. And our codes still have polynomial time construction and fast decoding and encoding algorithms. So such a result was proven before for binary erasure channel. But what we do is we prove it for an arbitrary binary memberless symmetric channel, which is a much more general universe of channels. All right, let me go on with describing what actually polar codes are and what is polarization. Before that, we'll still need a couple of more definitions. So first is the entropy. Imagine we have a channel W and consider a random variable X, which is uniform over bits 0, 1, and a random variable Y, which is the output of the channel if X is sent as the input of the channel. And then the entropy of H of W is defined as, the entropy of the channel H of W is defined as conditional entropy of the input X given the output Y of the channel. So basically, this corresponds to how well you can predict the input of the channel if you know the output. And then the Shannon capacity of W is going to be 1 minus entropy of W. All right, so let's finally start with some polarization. And for that, we need to consider the following picture. Imagine that we have n bits U1 to Un, which are IAD uniform over bits 0, 1. And we apply some invertible linear transformation, AN, to them, some invertible matrix, multiplied by some invertible matrix, and obtain n bits x1 to xn. And it's not hard to see that x1 to xn will also be ID uniform over bits 0, 1. And after that, we send these bits through the channels W and obtain the output vector y1 to yn. So from the previous slide, we know that the conditional entropy of xi given yi is just, by definition, the entropy of the channel W. And let's also look at this quantity, which is the conditional entropy of xi given all the previous bits x1 to xi minus 1 and the output vector. This notation just denotes all the bits from x1 to xi minus 1. And since all the bits x's are completely independent, it's clear that this entropy will also just be equal to entropy of W. However, what we are going to be interested in it is the similar entropies, but with the bits ui. So we will look at the entropy of the bit ui, given all the previous bits u1 to ui minus 1, and the output vector. And while all of these entropies are equal to the entropy of the channel, it will turn out that these entropies usually will not be equal anymore. And this finally brings me to the definition of a polarizing transform. And we say that this invertible linear transform is polarizing if, for most indices I, this entropy of ui, given the previous bits and the output vector, is very close to 0 or 1. And let me make it a little bit more clear. And for that, we will need to define certain bit channels. So let's start with the channel W1. This is the channel that we see if we try to decode the first bit U1, given only the output vector. All right, so this channel will send U1 to the output vector. Then the second bit channel W2 is the channel that we see if we try to decode the second bit U2, given the output vector as the previous bit. So this is exactly the channel that will send the bit U2 to the output vector and U1, and it will consider all the rest bits as completely random. And in the similar flavor, we'll define the bit channel Wi, which will send the bit ui to the output vector as the previous bits, considering all the next bits to be completely random. And again, this is the channel that we see if we try to decode the bit ui, given the value of the output vector and also given the values of all the previous bits. And so it is quite easy to see that the entropies of these bit channels, just by definition, will be these conditional entropies of bits ui given the previous bits and the output vector. And then we can reformulate our definition of a polarizing transform. And we say that the transform is polarizing if most of these bit channels have entropy somehow close to 0 or 1. And through the rest of the talk, we will be interested in the following notion of which will denote delta, and we will track the fraction of unpolarized channels. So again, we will say that the bit channel is polarized if it has entropy somehow close to 0 or 1, or otherwise we will call that the channel is unpolarized. And we'll be interested in this fraction of unpolarized bit channels. All right, so why are we actually interested in this polarizing transform is the following. It turns out that one can use a polarizing matrix to actually construct a linear capacity achievement codes. And unfortunately, I will not be able to cover all the details here and explain the connection in more depth, but basically we have the following relation, that if you have a polarizing matrix, which has a delta fraction of unpolarized bit channels, this will correspond to a linear code which has a rate delta close to capacity. And which means that if this fraction of unpolarized bit channels is small, the code will basically approach capacity. And so what Arikan did in his work is he showed how to actually explicitly construct such polarizing matrices for this delta fraction tends to 0. And then he actually constructed polar codes using these explicit polarizing matrices. So next, let me actually tell you a little bit more of how he actually constructed these matrices. And he did it in a recursive way by using some basic 2x2 transform. So this is the same picture as it was before, but here we'll have only 2 bits and 2 copies of the channel. And the linear transform here, which we use, is just going to be the matrix 1, 0, 1, 1. And we will call this transform as the kernel. Then there are 2 bit channels here, which we can denote as W minus W plus, defined similarly as before. And it is quite easy to see that the entropies of these bit channels will slightly polarize. And what I mean by that is that the entropy of W plus will be smaller than the entropy of the initial channel W, and the entropy of W minus will be larger, which means that the entropies of these bit channels moved towards the ends of the interval 0 and 1, which is exactly what we called polarization. So this transform slightly polarizes the channel. So what Arikan did in his construction is he used this basic polarization transform recursively in a way which I'm not going to describe here, but you can see schematically how it happens. So we can use this transform recursively, and in the end, if we denote everything that is happening here as one large linear transform, Arikan proved that basically this transform is polarizing, and therefore the polar codes that he can construct out of it are capacity achieving. So let's return to this relation that we talked about, that if we have that the fraction of unpolarized bit channels is delta, that results in codes or polar codes with rate delta close to capacity. So Arikan showed that for his construction of codes or polar codes, delta tends to 0 as you take larger block lengths or as you go deeper in the recursion. And but for polynomial convergence to capacity, which we desire, we want something stronger, and we want delta to be at most around 1 over n to the power 1 over mu, where mu is this scaling exponent that we were interested in. And I also told you that it was shown that for polar codes, this scaling exponent can be taken as at most around 4.7. However, there is a converse result, which says that for these polar codes, the scaling exponent is at least 3.5. So this is a limitation on these polar codes. Recall, however, that our goal was to get the optimal scaling exponent, which is 2, and we actually claimed to get that. And the way we do it is by considering some generalization of polar codes. And specifically, what Arikan used in his recursive construction is this basic 2x2 polarization transform. As it turns out, it is possible to actually use larger base transforms in the recursion. And what I mean is that we can consider an L by L transform, L by L kernel, and then apply recursion in a similar way for this transformation. And it will result in the whole big matrix to be also polarizing, which will again lead to capacity achieving codes. And this method has been proven to actually work in the sense that for at least for binary erasure channels, it was shown that scaling exponent decreases if you take larger kernels. And for example, in the latest work of Yao, Fazeli, and Vardi, they showed that you can achieve scaling exponent to be below 3 if you take the kernel size to be 64. And moreover, there was a result which showed that scaling exponent actually approaches the optimal value of 2 over QRE erasure channels, where Q is the size of the input alphabet. And this is proven for the regime where both size of the alphabet Q and size of the kernel L increase. But it was later improved by a great work by Fazeli, Hassani, Mandeli, and Vardi, who showed that this kind of exponent approaches the optimal value of 2 over a binary erasure channel as you only increase the size of the kernel. And this brings me to our result again. So what we proved is that scaling exponent approaches the optimal value of 2 as you only increase the size of the kernel. And this works for an arbitrary BMS channel, which is again a much more general universe of channels. All right, and in the remaining time, I will briefly describe what were the key ingredients which we used to prove this result. Recall this relation again, that the fraction of unpolarized channels is actually the gap to capacity that we obtain. So the key insight in polar coding is that the speed of global polarization, the speed with which this delta tends to 0, is completely dictated with how this polarization happens at a local level, and specifically how fast polarization happens for this one local kernel K that we then use recursively in the construction. So it actually suffices to prove that polarization happens locally to prove that polarization happens at a global level, and then to get fast convergence to capacity. And to be more specific, it turns out that it is enough to prove the following for the kernel K that we used in the construction, that there are only order squared L unpolarized bit channels, and all the other channels are polarized. Until the end of this talk, we'll call this property that there are only order squared L unpolarized bit channels. We'll call this property a strong polarization, that the kernel strongly polarizes the channel. So this approach was taken by Fazeli et al., where they proved the result for a binary erasure channel. And specifically, what they proved is that if you take a random kernel, which is large enough, then this strong polarization property will hold for any channel W prime, which is a binary erasure channel. So no matter what the erasure probability is, this kernel will strongly polarize this channel, in the meaning that this will hold. And as it turns out, if the initial channel W is binary erasure channel, then proving this for any W prime which is also binary erasure channel suffices to show that polar codes will have optimal convergence to capacity. So what we wanted to prove is that this local polarization happens for when the initial channel W is an arbitrary BMS channel. But this corresponds to proving that this strong polarization property holds for every BMS channel W prime, which we have here. But the problem we face here is that the universe of BMS channels is just too general. And for example, the size of the output alphabet is just not limited. And in our construction, we will actually face BMS channels with exponential size of the output alphabet. So this is just a very hard task to prove that there exists a kernel which will strongly polarize all the BMS channels universally at the same time. And the approach we take to overcome this issue is that we actually use different kernels throughout the construction. To illustrate this, this is how the construction worked before. So we have the same kernel K, which strongly polarizes the channels that it sees, and we use this kernel throughout the construction recursively. And what we do is we actually use different kernels at every stage of the construction. And specifically, at any stage, we choose the kernel that strongly polarizes the channels that it sees in the construction. And again, working out all the details, it is possible to show that if indeed every kernel strongly polarizes its corresponding channel, then the strong polarization will hold for the whole big matrix, and this will result in polar codes with near optimal convergence to capacity. And then the main claim that we need to prove is that actually for any BMS channel, there exists a kernel that strongly polarizes it. And this is what we prove. We prove that for any BMS channel W prime, if you take L, the size of the kernel, to be large enough, and you take a completely random invertible L by L kernel, then strong polarization will hold. And specifically, we prove that the first bit channels at the top here will be extremely noisy and have very high entropy. The last channels at the bottom will be almost noiseless and have very small entropy. And we prove that there is only order squared L channels in the middle, for which we do not claim any polarization at all. And again, the crucial part here is that this transition happens very sharply and that there are only square root L channels in the middle. And this square root L will then correspond to having only square root N channels, which are unpolarized for the big matrix, which will then lead to codes that approach capacity optimally fast. All right, so in the remaining part, I would like to describe the actual key technical ingredients that we used to prove this theorem. And it is actually completely unrelated from the context of polarization and polar codes, and it just concerns bit decoding for random linear codes. So consider the following picture. We have a random K by L matrix G, and we try to use it to communicate in the following sense that we have a random message of V of K bits. We'll multiply V by the matrix G, obtain the code word X, send it through L copies of the channel, and obtain the output vector Y. So again, this is just using a random linear code to communicate, since the matrix G is random. So as it turns out, we can connect the entropies of the bit channels that we saw before with the following quantity, which is the entropy of the first bit, V1 of the message, given the output vector. And so we will only deal with these entropies right now. And to prove the sharp transition, which I showed before, we needed the following two statements. First is that if the rate of the code, which is K over L, is below capacity by 1 over square root L, then this entropy of the first bit given the output vector is very small, which means that you can predict the first bit pretty reliably. But this is actually nothing new because it directly follows from Shannon's theorem, who showed that if you take a random code or random linear code with rate below capacity, then you can reliably decode the whole message, and then you can definitely decode the first bit as well. But for the second part, what we needed to prove is that if the rate of the code is slightly above capacity, so even if it's only 1 over square root L above capacity, then the entropy of the first bit given the output vector is extremely close to 1, which basically means that the first bit is unpredictable. So before that, what we knew from converse Shannon theorem is that if the rate of the code is above capacity, then you cannot reliably predict the whole message V. But what we needed and what we proved is that you cannot even predict the first bit of this message much better than just flipping a coin. And this is actually the key technical ingredient that we use to prove our result. All right, so this brings me to the summary. What we did is we constructed a variant of polar codes with almost quadratic rate of convergence to Shannon capacity, which means that our codes can have rate epsilon close to capacity and have block lengths almost quadratic in 1 over epsilon. And we proved it for an arbitrary BMS channel W. And the key ingredients that we used is we used large kernel size in the construction of polar codes, and we also used multiple kernels. And the key technical tool that we used was strong converse for bit decoding for random linear codes. All right, so there are a few further questions listed on the screen, but this is going to be it for me. Thank you.